Welcome to this explainer. Today, we're diving into an absolutely profound cosmic mystery. Literally right now, in 2024, brand new astronomical data is threatening to completely break our standard model of the universe. I mean, we're standing right on the edge of a massive revolution in fundamental physics, and we're going to explore exactly how and why this is all happening. So, just to set the stage for a second, when you look up at the night sky, you see stars, planets, glowing clouds of gas, you see galaxies. But how much of the actual universe are you really seeing? What makes up the vast, overwhelming majority, like 95% of our cosmos? Okay, let's dive into this because the answer is truly staggering. Honestly, it's a little humbling. Everything we have ever seen, touched, or interacted with, every star, every planet, you, me, literally your morning cup of coffee, all of that makes up a measly 5% of the universe. The rest? It's completely invisible to us. Roughly 27% is dark matter, and a massive 68% is dark energy. It's just wild to think that the normal matter we study in chemistry and physics classes is just this tiny, tiny sliver of reality. Section 1. The cosmic tug-of-war, dark matter versus dark energy. So these two unseen forces basically dominate existence, and right now, they're locked in this titanic, universe-spanning battle. Think of dark matter as an attractive force. It acts a lot like a cosmic cement that holds structures, like galaxies, together. It pulls inward, ensuring that those giant spinning galaxies don't just fly apart into nothingness. Now, dark energy, on the flip side, is a repulsive force. It acts like a sort of anti-gravity that's uniformly distributed throughout empty space, and it's driving the ever-accelerating expansion of the universe. So you've got one pulling things together locally, and the other pushing everything apart on a massive cosmic scale. But here's the really humbling part. Despite proposing all these cool theoretical ideas, things like weakly interacting massive particles, or WIMPs, and axions for dark matter, or a cosmological constant for dark energy, our actual understanding of both is heavily classified as very limited. These are highly theoretical guesses right now. I mean, they make up 95% of everything around us, yet they've never been directly detected in a laboratory. They are, for sure, the ultimate black boxes of physics. Section 2. The Standard Cosmological Model, the Reign of Lambda CDM. For a long time, cosmologists thought they had at least figured out the mathematical rules of the game here. The absolutely crucial point is understanding lambda CDM. This has been the concordance model, basically the gold standard in cosmology since the late 1990s. It neatly marries two concepts: cold dark matter, which provides that gravitational scaffolding for galaxies we talked about, and lambda, which is Albert Einstein's famous cosmological constant, representing a static, unchanging dark energy that's pushing the universe apart. And for decades, this mathematical model beautifully balanced almost all of our cosmic observations. Now, within lambda CDM, the behavior of dark energy is defined by an equation of state, which physicists represent with the letter W. And in the standard model, W is exactly equal to -1. This acts as a rigid cosmic speed limit. It basically means the density of dark energy never changes over time. It's constant. It's stable. No matter how huge the universe gets, the energy of empty space remains exactly the same per cubic meter. Section 3. The Fall of Lambda, the 2024 plot twist. So what happens when our most powerful new telescopes tell us that the standard model is just wrong? Let's trace this chronologically. Back in 1998, we first discovered the universe's expansion was accelerating, which is what really cemented that lambda CDM model in the first place. Then, between 2013 and 2019, an incredible project called the Dark Energy Survey mapped a massive chunk of the southern sky, specifically looking at galaxies and supernova. And then, in 2024, they released their final analyses, and suddenly, that perfect model cracked. A recent paper looking at this data used a beautifully dramatic Latin phrase, the annus horribilis of lambda, literally a horrible year for the cosmological constant. The new data showed a 3.2 sigma deviation from our standard model. To put that into perspective, in statistics, a 3.2 sigma deviation means there's less than a 1 in 700 chance that this observation is just some random fluke. In physics terms, that is a massive, glowing red flag that our core assumptions might be fundamentally flawed. Now, what's really interesting about this is that both the Dark Energy Survey and the Dark Energy Spectroscopic Instrument, or DESI, looked at standard cosmic rulers, things like the brightness of supernovae and the ripples in galaxy distributions, which we call baryonic acoustic oscillations. Their data strongly suggests that dark energy is not a constant. Instead, it prefers a model called W0WACDM, which is just a technical way of saying dark energy is actually evolving and changing over time. It's behaving in ways that Lambda CDM said it absolutely shouldn't. Section 4. Phantom energy and big rips. Breaking the cosmic rule. Okay, so if dark energy is actually evolving, that means our rigid cosmic speed limit is broken. Remember how W is supposed to be exactly -1? Well, if dark energy is evolving, the data suggests W might actually dip below -1. And if that happens, we cross into this highly unstable, almost sci-fi theoretical territory known as phantom energy. And guys, that opens the door to some truly terrifying, yet totally fascinating possibilities for the ultimate fate of our universe. If phantom energy is real, the future of our universe is, well, unimaginably violent. Unlike a constant dark energy, the density of phantom energy actually increases as the universe expands. It creates this runaway feedback loop. The expansion accelerates so rapidly that it reaches infinity in a finite amount of time. This is what physicists call the Big Rip scenario. First, galaxies are torn apart, then stars, then planets. Eventually, the expansion becomes so incredibly powerful, it literally rips apart individual atoms. And finally, the very fabric of space-time itself. Section 5. The dark fluid hypothesis, a unified theory. So, our standard model is breaking, and the alternatives look incredibly apocalyptic. But what if we're just looking at the math all wrong? Actually, think about this. For decades, we've treated the cosmic cement and the anti-gravity as two totally different, completely mysterious substances. But what if dark matter and dark energy are just two sides of the exact same coin? This mind-bending question is the core of the dark fluid hypothesis. Imagine the entire universe is filled with a single, continuous substance, a dark fluid. Where this fluid pools together in high concentrations, like around galaxies, it behaves like an attractive force. It acts just like dark matter. But out in the massive, empty voids of deep space where the density is extremely low, the fluid sort of relaxes. It acquires a negative pressure, and it begins to act as a repulsive force, driving expansion, just like dark energy. It's an incredibly elegant idea, right? Modeled through complex scalar fields, which you can kind of think of like a giant temperature map across the universe where every single point in space has a specific value. This unified dark fluid naturally produces a continuous range of attractive and repulsive qualities purely based on its local environment. It even manages to reproduce the mathematics of other fringe theories like modified gravity. And most importantly, it offers a real, viable replacement for the shattered Lambda CDM model, all without requiring two completely separate, invisible mysteries. We are absolutely living through a profound moment in science where the fundamental rulebook is actively being rewritten. This 2024 data has exposed the cracks in our understanding of 95% of reality. So I'll leave you with this. As new data continues to pour in, will we find that our universe is destined to end in a catastrophic phantom energy big rip? Or will we discover that we've spent our whole lives swimming blindly in an elegant, undiscovered dark fluid? The cosmos is keeping its secrets for now, but we are definitely getting closer. Keep your eyes on the stars, and as always, stay curious.